Hey everybody, hope you're well. It's Dr. D. We're back. We're talking about discrete probability distributions today. We're talking about the Poisson distribution, just so you know where we are. See if we can't do a little as previously seen on as quickly as we can. So what are we talking about? Well, we talked about descriptive statistics a while ago. We're working our way up to inferential statistics, right? Making guesses about the world that we can't see, right? The big, vast world that our lack of omniscience, our human blinders prevent us from being able to see, by using the world we can see, samples, right? We can look around, look outside, look in your house, right? Look within, to try to make some guesses about the wider world. And we're hoping for these to be intellectually responsible guesses. In order to do that, we're going to need some tools, some mathematical tools. And right now what we're working on is our probability skills and our understanding of how probability works. Now with probability, we talked about random experiments. Random experiments are where we start. We said any experiment where we can exhaustively list all the outcomes is a random experiment. These outcomes are also called sample points, right? We're trying to think about sets. We're drawing sample points from a sample space. So the sample space is where these all come from. And so if you have all of the sample points, they make up the sample space. So these are the outcomes that we are working with, and that's part of it. But in order for us to be calling this probability, we have to assign probabilities to these. Each outcome has a probability. They all have to add up to 1. And we talked about a couple ways of assigning probabilities. The classical method, that's where you just divvy it up evenly, like with flipping coins or rolling a die or drawing cards. There's also the relative frequency method. We talked about relative frequencies a while ago. There's also the subjective method, which is just making it up. That works particularly well when you have not a lot of good data to work from. You have to make an educated guess, so ideally as educated as possible. And then we also talked about, last time in the last video, we talked about some ways to use theory, right, to think about these things, to model it. And so that's what we're going to be doing today. We're going to be doing some modeling. The one we've looked at so far is binomial experiments, and binomial experiments are related to Poisson distribution. So let's see, how does the binomial experiment work? Well, binomial experiments were when we had a bunch of independent trials, different independent trials, and each trial had a possibility of success or failure, and X was the number of successes in n trials. They're independent, I already said that. What else? Oh yeah, P is the probability of success. And so we talked about these at some length. We worked our way through the intuition behind this. There's lots of different ways to get there, and each of them is equiprobable, as it turns out, and so we can just multiply the number of ways to get there by the probability of a given way. But the last thing we talked about, or one of the last things we talked about, was the expected value of x, or mu. And we said, well, it's equal to n times p. This gets us close to Poisson. I'm not going to go into too much depth with the derivation here, but I want you to understand how these are linked, because this is not totally new. The intuition is similar, right? Now, in the example we looked at, this was 3 times a third, which equals 1. And these probabilities, these are always going to be between 0 and 1, right? That's how probability works. And generally, n is always going to be greater than 1, right? And what we're always going to have is we're always going to have n be bigger than p, right? And so in this case, we have kind of big-ish times smallish, and we get to a normal number, right? That's in between the two of them. But the same thing would happen if we did 30 times 1 over 30, right? That would also equal 1 on average, right? Same thing would be true if we did 300 times 1 over 300. Now these probabilities start getting unwieldy, though, and these n's start getting unwieldy. Partly because we're going to be doing factorials, but partly just because in practice, when we start talking about 300 independent trials, it's a different circumstance. That's not to say that the intuition isn't similar, but it's a different circumstance, right? Because you're probably not flipping a coin 300 times, right? Particularly when we talk about, let's say, 3 million times 1 over 3 million, right? It's hard to work with that. And the example we used to motivate the binomial distribution was a sales telemarketing, right? Sales calls. And now we're going to look at kind of the other side of the phone line. The other side of the phone line would be like a call center. So what are the random trials in this case? Well, anybody might call, right? Let's say, it's a Verizon call center. I'm not a big fan of Verizon, just going to lay that out. I had a bad experience a long time ago, but use them for the example. Anybody might call, right? Now, that if we treat each person like an independent trial, that means n is really large for every given second of the day, right? On the other hand, the probability of that happening for any given person, assuming we treat them as though they're identical, even though that's not true, but we can kind of model that, right? We can simplify it, use a simplifying assumption. The probability for any given person is really vanishingly small. But if we have, two numbers here, and we do, right? We have, what do we have? We have n, which is really big, times p, which is really small. What we showed here is that, you could take a really big number and multiply by a really small number and get moderate mean, right? Moderate average from those trials. And so the way that we treat this then, or the situation that we look at this in, is the number of occurrences over an interval, right? Because the number of occurrences over an interval, assuming that we don't know what the process is that generates these, is a lot like a really large number of Bernoulli trials, each of which has a very small probability of success. And so instead of getting n and p separately, like we did here, usually we just get the mu, right? So we're talking about the number of occurrences over an interval where mu is the average number of occurrences. And so this is the random variable that we're going to be interested in now. You can see that it's related to the binomial distribution. This is going to be our x then. X equals this whole thing. It's related to the binomial distribution, but it is different. They're gonna give us a little bit of different stuff, and it's gonna work out to be slightly different in terms of the calculation. So what might be some examples of this? Well, I already gave one, which is the number of calls to a call center in a given period of time. So let's say the number of calls in a 2-minute period. Right. So that's one example. Another example might be what? The number of customers at a drive-through in 5 minutes. What else? Maybe the number of thunderstorms in March. So these are things we can model, right? It's the number of occurrences, the number of 18-wheelers on a 100-mile stretch of highway. So this can be an interval in time or space as well. And so when does this work? When do we have... So a variable that looks like this will follow what's called a Poisson distribution. Poisson, I believe, is a French word for fish. Presumably some guy named Poisson discovered it. I'll look into it later. Google it, then you'll know. I wish I could just tell you, but I don't know. Okay, so what has to happen? Well, we have a few propositions that have to be satisfied. So what has to happen for a Poisson distribution? We have to have probability of occurrence be the same for any two intervals of a given length. So that's 1. 2. An occurrence is independent. Occurrence in one interval, or in each interval, is independent. There we go. There we go. So if we have these two, then x has a Poisson distribution. There we go. So rather than derive the distribution here, because it requires math that is interesting but perhaps not crucial, I'm just going to write the Poisson distribution function. Maybe some other time if a lot of people really want to know how we got it. I'll walk through the how we take. Basically, you can take the binomial distribution, which we know the intuition for because I talked about it, and you can use that to derive this Poisson distribution in the limit as n gets large and p gets small. But for our purposes, I could just write this down. So f of x, this is a probability function, right? So we take f(x) and we map it to a value. We can call that value f of x. So f is the machine that takes an x and spits out an f of x. And this is that machine. It's going to be mu raised to the x times e raised to the negative mu all over x factorial. Okay. So a few things here that might be new to you if you haven't been watching my other videos, or even if you have. Mu is the mean, and usually we need that in order to parameterize this function. X, we already established this is going to be the number of occurrences. E is Euler's constant. It's just a number. It's not a variable. It's 2.71828 and so forth. It's a really cool number. If it's new to you, Google it. There's lots of cool stuff out there about E. And then the factorial symbol, as stated before, 0 factorial equals 1, 1 factorial equals 1. Beyond that, it's the product of the number and all lesser numbers, right? So 3 factorial equals 3 times 2 times 1. 5 factorial equals 5 times 4 factorial, which equals 5 times 4 times 3 factorial. It's 5 times 4 times 3 times 2 times 1. You get the idea. That's how we do factorial. So let's do an example quick, just to kind of use this and see how it's used. Again, we're not going to go too in depth with the derivation, but we can get the idea. So let's say we have a call center, and historically, in a given 10-minute time period, so 10 minutes, they get 6 calls historically. And we want to know what the probability is. What's the probability of getting 10 calls in 10 minutes? Right? They just want to make sure we have enough staff to handle peak stuff, right? So what is the probability of this? Well, first we can parameterize this function now that we have mu. So our function here for this particular call center for 10 minutes is 6 raised to the x times e raised to the negative 6 all over x factorial. For this practice problem, or this scenario, we want to look at f of 10. So we're going to want 6 raised to the 10th power times e raised to the negative 6th power all over 10 factorial. Now remember, this is a probability, so it has to be positive. It has to be between 0 and 1. So that's a good way to check to see if you did it right. I'm just going to crunch these into the calculator. If you're doing this on your calculator, usually there's a e to the x key, right? So you should have a key that looks like that. Or if you're doing this in Excel, equals exp. Actually, let me see if I there's my task tracking sheet. Let's get a calculator up here, and we'll do the math together. All right, so we have 6 to the 10th power. That's a big number. And we have e raised to the negative 6. That's a small number. We want to take these and multiply them together. And this is our numerator, which again is a big number. Now we have our denominator, another big number, which gives us our f of x, f of 10. It's going to be our numerator divided by our denominator. 0.041303, 4.13% chance. So 0.0413. All right. So that's how you use a Poisson distribution. This is telling us that the probability of getting 10 calls in 10 minutes is 4%. What about some interesting stuff? Well, in this case, what the values that x can take are unbounded above, right? So x, well, we could get 0 calls, or 1 call, or 2 calls, or 3 calls, or 4 calls, or et cetera, et cetera, et cetera, right? 10, 20, 30, who knows? It gets very improbable as you get higher, but it's not impossible. It's just vanishingly small probability. So what do we do? Well, sometimes we might have a question or want to know what's the probability of getting 10 or more calls. Let's do 2 or more calls. 10 or more would just, the math would just be longer and more tedious, but so we want to know what this is equal to. Well, normally we would take f of 2 plus f of 3 plus f of 4, but the problem here is that this is an unending, an infinite sequence, right? That's just going to keep going forever and ever and ever. So what we can do is we can take advantage of the probability theory we learned before. The probability of 2 or more is 1 minus the probability of 0 or 1, right? Because this is the probability of not getting 2 or more, and then if we subtract it from 1, we get the probability of 2 or more. So we have 1 minus f of 0 plus f of 1. Let's go back into our Excel. Well, we can lay these out numerically first. So we have f of 0 equals 6 to the 0, that's mu to the 0, e to the negative 6 over 0 factorial. Oh, well, this is just going to be 1. 6 to the 0 is 1, 0 factorial is 1, so this is just e to the negative 6. Well, we already calculated that here, right? So let's call f of 0, it's just this one right here, right? Copy it and paste it, so that's f of 0, 0.2% chance. Okay, so that's that one. How about f of 1? Well, that's going to be 6 to the first times e to the negative 6 over 1 factorial. Well, 1 factorial is just 1, so this is going to be 6 times e to the negative 6. And so f of 1 is equal to 6 times this. All right, now we want to add these together. You get 0.002479 plus 0.014873. That gives us 0.017351. Add these together. You get 0.0174. So that's this part right here, 0.0174, which means that if we want to calculate this probability, this becomes 1 minus 0.0174, which is 0.9826. So there's a 98% chance that they will get 2 or more calls in a given 10-minute time span. So that's one thing to keep in mind, is that oftentimes, because it's unbounded above, because x is unbounded above in domain, we need to take the we need to subtract the probability of the complement. That happens a lot with Poisson. Other things with Poisson that you should know, yeah, some other cool stuff. So if we know that mu equals 6 for 10 minutes, what if we wanted to know the probability of getting 50 calls in an hour? Well, mu doesn't equal this anymore, right? Mu is a totally different distribution, right? So if it's 6 calls for 10 minutes, an hour is 60 minutes, so we have a new mu, which equals 6 times our old mu, right? Which is 36. If they get 6 calls for 10 minutes, then they get 36 calls per hour. And so that's what I'm going to be dealing with here. 36 calls per hour. Now we have a new function. F of x equals 36 to the 50th power times e to the negative 36th power, all divided by 50 factorial. Okay. I'm not going to crunch those numbers. You can do it with a powerful enough calculator. And I did it a while ago. It's 0.004983. Okay, but you can do that for larger time periods. You can also do 5 minutes, right? Mu would be 3 for 5 minutes, right? Just because that's, 6 for 10 minutes, 3 for 5 minutes. And so a lot of times, if you want to know about another interval, you can just transform the one that you already have. All right. Last thing I want to tell you guys is, okay, the short way to get expected value. Well, the expected value is almost always given in these scenarios, right? You use the relative frequency method a lot of times to calibrate this. So expected value, the expected value of x equals mu, which is given. To calculate the variance, sigma squared. Well, the Poisson has a unique distribution that is also equal to the mean. That is not generally the case, but for Poisson, this is the case. The expected value is given, and the variance is equal to the expected value. There are other similar count variable or count distributions which can work if you know this isn't the case. Not the case. If you know this is not the case, I don't have a video about this. Google it, you'll find it. But the negative binomial is the other one, the other good count distribution that is useful, and that can account in ways for this this unequal variance and mean. So there you go. I hope you guys found this useful. We have Poisson distribution. It's a probability of a number of occurrences occurring in a given interval in either time or space. It's related to the Poisson distribution, or to the binomial distribution, but it has a really big number of trials, a really small probability for each one. And this is the function we use. The only new stuff really that's super new is just being comfortable with your x to the y key on your calculator, or knowing that you can use the caret in Excel, and then the e to the x, or the exp function in Excel, as well as factorial. That's right, I didn't mention this, but equals fact is the Excel formula for factorials. So there you go. Hope you guys found this useful. Again, I'm Dr. D. If you have questions, please let me know. Send me a message on YouTube, or leave a comment in the comment section, and I'll be happy to do whatever I can to help. Thanks, guys. I'll see you next time. Bye.